Good morning. Now we will start by derivatives. First, by definition, we have f prime of a is equal to the limit as x tends to a of f of x minus f of a over x minus a. In the example, we have fx equal 3x minus 2. We want to find f prime of 3. By definition, we have limit as x tends to 3, fx minus f of 3 over x minus 3. f of x, it is 3x minus 2. f of 3, we substitute 3 in the function. 3 times 3 is equal to 9. 9 minus 2, we get 7 over x minus 3. Now we have 3x minus 9 over x minus 3. If we substitute here, we will get 9 minus 9 over 3 minus 3, so it is 0 over 0 indeterminate form. When we get 0 over 0, we should factorize in order to get rid of the indeterminate form. So we have limit as x tends to 3. In the numerator, we can take 3 as common, x minus 3 over x minus 3. So we cancel x minus 3 by x minus 3, so the answer will be 3. Now to study the differentiability at a point, we say that f is differentiable at x equal to a if f prime at a minus equal f prime of a plus. We mean by this if it is right differentiable and left differentiable. For an example, fx equal x if x is positive, minus x if x is negative, and 0 if x equal to 0. Study the differentiability at x equal to 0. So we should find f prime of a minus if it is equal 0 minus if it is equal f prime at 0 plus. By definition, f prime of 0 minus, it is limit as x tends to 0 minus of f of x minus f of 0 over x minus 0. Here we have x tends to 0 minus. 0 minus, it means that x is less than 0. We take this interval, which is x less than 0, and we put the answer, which is minus x. Minus f of 0, here we have f of 0, so the answer is 0 over x. Here we have limit as x tends to 0 minus. So the answer is limit as x tends to 0 minus x over x. We can simplify, so the answer is minus 1. Now f prime of 0 plus, it's equal limit as x tends to 0 plus f of x minus f of 0 over x minus 0. Limit as x tends to 0 plus, 0 plus, it is a number greater than 0. We talk about this interval, then f of x is x. So the answer will be limit as x tends to 0 plus x minus 0 over x minus 0. It is limit as x tends to 0 plus x over x. We can simplify, then the answer will be 1. So f prime of 0 minus, it is minus 1. F prime of 0 plus, it is a plus 1. So f prime of 0 minus is different than f prime of 0 minus, and 0, here is 0 minus, then f is not differentiable at x equal to 0. Now, according to the rules which we use most in the functions in order to get table of variation and other things. First, we have if f of x equal to constant, where a is constant, then f prime of x is equal to 0. If we have f of x equal x, imply f prime of x is equal to 1. In general, if f of x equal x power n, imply f prime of x is n x power n minus 1. Example, if we have x power 3, we want to make derivative, so the answer is 3x squared. In the same way, we can get if f of x equal ax power n, where a is constant, implies that f prime of x equal, we keep a multiplied by n and make n minus 1. Example, if we have 4x power 2, derivative of 4x power 2 is 4 times 2 and x equal 8x. Now if we have u times v, two functions in x, u times v equal u prime v plus v prime u. Simple example, 2x plus 1 times x plus 3, we want to make derivative. We can write first here u is equal to x plus 1, then u prime equal 2, v equal x plus 3, v prime is equal to 1. Now according to the rule, which is u prime v minus v prime u, u prime it is 2 times v, which is x plus 3, plus v prime it is 1 times u, which is x plus 1. Now we should simplify the expression, plus 2x plus 1, and the answer will be 4x plus 7. Part 6, we have u over v. The derivative of u over v is u prime v minus v prime u over v square. Example, 3x over x plus 1. We have u is 3x, u prime equal to 3, v equal x plus 1, v prime equals to 1. The rule is u prime v minus v prime u over v square. U prime is 3x times x plus 1. Sorry, here we have only 3 minus v prime times u over v square, which is x plus 1 square. If we expand here 3x will be cancelled by 3x, so the answer will be 3 over x plus 1 square. Part 7, radical. We have radical, in general, radical u. If we make derivative, it is u prime over 2 radical u. Example, if we have radical x plus 3 and we make derivative, here u is x plus 3. The derivative of x plus 3 is 1. 1 over 2 radical x plus 3, and we have a special case which is radical x. The derivative of x is 1, so the answer is 1 over 2 radical x. And we have a special case of the constant when we apply u over v. If we have k over v or k over x, if we make derivative, the answer will be minus k. K is a constant number over x squared. This is a special case of part 6. Now we have continuity. F is said to be continuous at x equal to a if we have f of a equal limit as x tends to a minus of f of x equal limit of f of x as x tends to a plus. Here we say that it is right, and here we have left continuous. Let f be a function defined over R by f of x equal x squared plus 2x minus 4 if x is greater than or equal greater than 1 and x squared minus 3x plus 1 if x is less than or equal to 1. We want to study the continuity at x equal to 1. First we have to calculate limit as x tends to 1 minus. We need to substitute 1 where x is less than 1, which is here in this interval. Limit as x tends to 1 minus of x squared minus 3x plus 1 equal 1 squared minus 3 times 1 plus 1 equal 1 minus 3 plus 1, and the answer is minus 1. Limit as x tends to 1 plus, we will substitute 1 in the first equation equal limit as x tends to 1 plus, where 1 plus it is x greater than 1 of x squared plus 2x minus 4 equals 1 squared minus 2 times 1 minus 4, 1 minus 2 minus 4 equal minus 5. Here you can see that the two answers are different, so no need to calculate f of 1. f of 1, it will give minus 5. So we have limit as x tends to 1 minus of f of x is different than limit as x tends to 1 plus. So f is not continuous at x equal to 1. Here we have an important note. For a polynomial function, if f is not continuous, then it is said to be a gap point. Example, if we have limit as x tends to 1, 1 minus equal to 3, and limit as x tends to 1 plus is equal to minus 1. So the curve will be in this way. For example, here we have 1 minus is here, and 1 plus is here. 1 minus, limit as x tends to 1 minus is equal to 3. Here we have 3. For example, the curve in this way. Here we have 3, and at 1 plus it is minus 1. We have here it is a gap point. The function is not continuous at x equal to 1. And in case of rational function, if f is not continuous, then we will have a vertical asymptote. For example, here we have x equal to 2. The function will be divided into two curves. For example, this is the first curve and this is the second curve. We can see that the function is continuous at any point except at x equal to 2, which here we have x equal to 2 is a vertical asymptote.